Why is, okay. So that's set up, that is set up. Wait another minute or two. All right, how many people are logged on? I'll wait another minute or two. Okay, so first, any questions about the thin film software? Any difficulties that people encountered with it? No, it was straightforward. All right, so the next time what you'll be doing with the thin film software is you'll be putting together many alternating layers, and you're going to try two different cases. And you should find in both cases that you get a reflection stop band. A stop band just means a band of wavelengths in which, or a range of wavelengths in which you can't get any light propagating through the system because there's very high reflectance. And you should find that the width of that stop band depends on the refractive index contrast. because if you have a very large refractive index contrast, then you get very strong reflection. And if you have a small refractive index contrast, meaning that the two layers have almost the same refractive index, then you get very weak reflection, and so you get a narrow stop band. All right, what we're going to talk about today and part of Thursday is diffraction gratings. So it's going to be kind of like the upcoming assignment in that you have a periodic system, but it's going to be periodic perpendicular to the direction of the wave rather than periodic along the direction of the wave. And the basic idea is quite simple. You've got a whole bunch of very narrow slits separated by a distance d, and when you send light through them, you get a series of very sharp peaks. And the angle at which you get those peaks depends on the wavelength of the light. So if you look here, we see light spreading out through a grating. We have several wavelengths coming together. Then they pass through the grating and they get dispersed. And the angle at which they go depends on the wavelength. And so this is a very practical thing in that you could separate out light by its wavelengths. You could look at, instead of using the wavelength to predict the angle, you could use the angle to determine the wavelength. And so people have been using these for a long time. And one classic thing to do is to send the emission lines of different elements through them. And you see some background light from the source, and then you see the strong emission lines of the element. And you get different lines from different elements. This is how people determine what kinds of elements are in the outer surface of a star. So diffraction grades are very important in astronomy. And they're used anywhere else that you need to figure out the wavelength of light coming from some sort of specimen. Basically, if you look here at the concept, source, grating, now you get several bands because you get several peaks. And so if this was a blue wavelength, then a red wavelength would produce a peak that's kind of here, and another peak that's kind of there, and another peak that's kind of here, and another peak that's kind of there. So you get several of these. And all we would do is just put a whole bunch of little detectors along here or along here. Either of them will do, and we'll be talking about why you might choose one over the other. But you just put a bunch of detectors here, and you would know that, okay, if it goes at this angle, it's a blue wavelength. If it goes at this angle, it's more of a pale blue wavelength. If it goes at this angle, it's green. That angle, it's yellow, and so forth. And that's how people detect spectra all the time. Grating spectrometers are found in almost any lab you can imagine, because almost everyone, for one reason or another, needs to determine the range of wavelengths absorbed or emitted by a substance to learn something about its composition or to learn something about how the molecules in it are changing. So we're going to try to understand why it works as it does. Now, the very basic idea is quite simple. Each slit has width A, and we know that if I've got a source with a slit with width A, it produces a sinc function. But we're getting a sinc function from this one, and a sinc function from that one, and a sinc function from that one. So we're adding up a whole bunch of sinc functions. And these sinc functions have phase shifts between them. And that phase shift is e to the I ky sine theta, because the path difference between here and here would be d sine theta, and the path difference between here and there would be 2d sine theta, and the path difference between this one and that one will be 3d sine theta. So y is just d sine theta. And then we could factor out the sinc function. We've got e to the minus I km d sine theta, or e to the minus I k d sine theta raised to the m, or e to the minus I m phi. And if phi happens to be 2 pi or 4 pi or 6 pi, etc., well, then e to the minus im phi is just 1. So we're just adding up a whole bunch of 1s, and we get a sum that's equal to the number of slits. So the spectrum has peaks wherever that happens, all right? Wherever it is that phi is 2 pi times an integer, then 2 pi over lambda times d sine theta is 2 pi times an integer. So d sine theta is an integer times lambda. Now you would never want to use the center peak because all the wavelengths go to the center peak. So you're not going to get any discriminating power there. You're not going to be able to tell the difference between two wavelengths. But this one would do and that one would do. All right, so that's why we get constructive interference here and so forth. But then one important thing we need to understand is why is it that we get so little light in between the peaks? Before, all of the diffraction patterns that we looked at were very broad. You know, you had this gently changing diffraction pattern, peaks and minima, and nice smooth, gentle changes in between. Here, it's just sharp spike, practically no light, sharp spike, practically no light. Let's see, we've got n slits, and if phi were 2 pi over n, they would add to 0. And the way to see that is, here's, we'd have e to the I phi, e to the 2i phi, e to the 3i phi, e to the 4i phi, e to the 5i phi. It would be going around and around. And so each time we raise it to a higher power, we just rotate the angle by the same amount because we're getting e to the im phi. And if it were 2 pi over n, then when we add up n of those exponentials, we go around the circle once. So we're adding up complex numbers evenly spaced around the unit circle. Any questions on why that would happen if phi were 2 pi over n? Well, let's say the phi were twice that. Okay, well, then we add up this one, and 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 this one. So we still go around the unit circle. We make fewer stops along the way, but we definitely go around the unit circle. We actually go around the unit circle twice. And so we add up two things that add up to 0. And 0 plus 0 is, hang on, nothing and nothing, carry the nothing. I think that's a Firefly line originally. That's nothing. All right, so that explains those. Now, what if we're in between? Well, if we're in between, then it depends on how far we're in between. Say that we differ by, say that phi is way less than 2 pi over n. Okay, we add up one and another, and by the time we get through that whole cycle, we've just added up all of these points in the complex plane. These definitely don't sum to 0, right? Whereas if phi were much larger than what we've used here, but still less than 2 pi over n, we might add up, say, 3/4 of the way around. We get something that definitely isn't large, but it's also not 0. And so that's why these peaks are, they have a finite width to them. Any questions? So I've posted a Mathematica file on Blackboard. I'm going to give everybody a second to download it. It will be found under course documents. What? Stale sign-on request. All right, now let's try this. Somebody's posting something in the chat. Guess it's private message. I mean, there's one way to do this. You close the program, you restart it. All right, there should be a Mathematica file down here called Diffraction Grading. I'll give everybody another minute or two to download it and open it if you've got Mathematica on your computer. All right, so as always, we go in and we have to first hit Shift-Enter to run these commands, to store these things in memory. And we can play around with D and lambda, and we can play around with the range of angles. Here I've plotted from -20 to 20, but we could easily plot from -90 to 90. And we would see several spikes because D is 2 microns, lambda is 0.532 microns or 532 nanometers. And so we're going to get spikes when sine theta is an integer multiple of lambda over D. Well, lambda over D is slightly more than 0.25 because it's 0.532 divided by 2. So it's going to be 0.26. So we could get sine theta equals 0.26 or 2 times that, that's 0.52. Or 3 times that, that's 0.78, but we can't get 4 times that because we'd have sine theta greater than 1. So we get 3 spikes with positive m values, we get 3 spikes with negative m values. Now, let's zoom in on one of these spikes. This spike is around 50, 40, 30, 20, 10. So we're going to zoom in. We'll start going from 10 to 20. And then we're going to go between 15 and 16. Okay, this thing has non-zero width. Now let's see what happens here if I cut the number of slits in half. Right now, I get a 0 at, I would say, 15.35 and 15.5. So the width is about 0.15 degrees. Now I get a 0 right around 15.2 something, 26, 27, and 15.57. So from 0.27 to 0.57 is 0.3 degrees. So I cut the number of slits in half and I doubled the width. Conversely, if I were to add over half that range, now I go from 15.39 to 15.47, so roughly 0.08 doing this by eye. So I double the number of slits and I go from 0.15 to roughly 0.08. So I double the number of slits and I roughly cut the width of it in half. Any questions or comments? Does this remind you of anything? Does this look like anything we've seen before?
Spread function?
Point spread function, yeah. The wider the aperture, the narrower the point spread function, and vice versa. Every diffraction pattern, the wider the aperture, the narrower the diffraction pattern, and vice versa. So we're just seeing the exact same thing here. Now, this has implications, all right? This has implications for instrument performance. Suppose I wanted to look at two wavelengths that were separated by 1 nanometer, right? I want 1 nanometer resolution. And for one reason or another, I've decided to work with one of the peaks that's farther out. Okay, so we're going to start with 50 slits. And when we work with 50 slits, we are going to find that with 50 slits, even though there are really two lines, there's lambda 1, there's lambda 2, which is lambda 1 plus d lambda, and we're adding up the profiles from two things here. You can see that what we're plotting is the sum of these two intensities. We can't tell them apart. So I double it, and I can tell now that well, if I have a really good detector, meaning that I have very narrow pixels, I've spread this out a whole lot, and I have really good signal to noise, then I could begin to tell that we've got two wavelengths. So I double it again. I use a wider grating. Now, I could tell reasonably well that I've got two wavelengths. Again, it's going to depend on how small my pixels are. It's going to depend on what my signal to noise is, but in principle, I should be able to do that. And if I had 400 slits, then this is a really long sum to compute. Then I can tell quite clearly that I have two lines. So if you want to do very high precision work, then you need very, very wide diffraction gratings. And that doesn't just mean that you go and buy a bigger diffraction grating. It also means that you have to be able to take whatever light you're collecting and spread it out over that wider grating and produce a well-collimated beam that hits that grating. If you had the light go through a really lousy lens with lots of aberrations, then you're not going to get nice collimated light hitting. You're going to get light hitting it over a range of angles. And if it's hitting it over a range of angles, then it's going to come out, even if it's a single pure wavelength, it's going to come out at a range of angles. So this can be hard to work with, but that's the basic idea. And we're going to talk later about how to predict more quantitatively what this resolution is. Any questions so far?
So when you're adding more slits to this diffraction grating,
yeah,
you're kind of increasing the destructive interference around those individual peaks, and that's
exactly
what gives them the resolution. Cool.
Exactly. If you have two things that differ by a small phase shift, that in and of itself does not give you destructive interference. What gives you destructive interference, it's not this wave and this wave from two adjacent slits that interfere destructively. What's, if you're just a little bit off angle, what's interfering destructively is this. It's going around the whole circle. It's the fact that you've got this wave and this wave, that you've got this wave and this wave. So you need to have enough slits that whatever that phase difference is, you're going to add that phase difference to twice that phase difference to 3 times to 4 times until eventually, 100 times that phase difference winds up being a half cycle. Because the difference between two time slits the difference between two slits, the phase difference between two slits could be just a minuscule fraction of a cycle. It could be 1/100th of a cycle. But 50/100ths of a cycle is half a cycle. So that's what you need this for. That's why you need so many slits, which means you need to spread out the light really well. And I see a comment in the chat about looking at things several million parsecs away. Honestly, once it's pretty far away, once it's, you know, the next solar system away, that light is pretty much all coming in at almost the same angle unless you have a very wide telescope. So that's not the issue. The issue is you've collected all of this light. Collecting almost always means collimating. Then you might have to expand the light because, you know, normally you want to collect from a very wide area and focus light from a very wide area onto a single pixel, right? Or onto a few pixels, right? The point is that you want to have this light from a very wide area on just a few pixels, and then light coming in at a slightly different angle from a wide area would again be on just a few pixels. So it's all about collimating light. Well, now you got to take it and spread it out nice and evenly over a grating. And I'm not an expert on how people do that, but that is the challenge, to get the right beam width so that you can cover the whole grating. And this is how people tell things about, say, isotopic abundances in the galaxy. All right, this is how they test hypotheses on the ratio, or this is one of the ways in which they can test hypotheses about, say, ratios of isotopes, is that you could say, all right, this isotope, I mean, one way, of course, is just sampling what's in the solar system. But that's going to tell you about the abundance of elements in this region of the galaxy after a few generations of stars. But another thing you could do is you could say, all right, we think that this molecular cloud has, I don't know, carbon monoxide in it. And if it's this isotope of carbon, it's going to have this vibrational spectrum. If it's that isotope of carbon, it's going to have that vibrational spectrum. And so if they have good enough signal to noise, and I'm not an expert on how often they're actually able to do this, but when they have good enough signal to noise, then in principle, you could tell the difference between two different isotopes by looking at the vibration spectra of a molecule and saying, all right, what spectrum, which isotope was in that molecule, because the mass ratio will determine how the frequency at which those chemical bonds vibrate. I don't know how often they're actually able to do that. You know, maybe Dr. Povich and Dr. Binder would say they're almost never able to do that. What I'm telling you is that, at least in principle, when you get the right signal to noise, this is something you could do. I know that, let me think. I know that people have done very, very high precision spectroscopy on the surface of the sun. All right, that's one place where signal to noise is really not an issue at all. Other questions on this?
So as long as the slits are all covered by the incoming light, you'll be able to get this resolution?
Exactly.
Okay.
Making a very wide aperture diffraction grating is nowadays not that hard for the most part. What's, you know, the harder part is just going to be getting the light to spread out. I mean, I can, on campus, you got plenty of demonstration diffraction gratings that are several centimeters wide. That's not a problem at all. If the spacing between the slits is a couple microns, you know, we've got 10 to the minus 2 meters over 10 to the minus 6 meters. We got 10,000. So that's a cheap diffraction grade. People can make even wider than that. To see maybe in a different way why it is that adding up waves with these evenly spaced phase shifts produces zero, here I've got 3 waves separated by 1/3 and 2/3 of a cycle. Here we've got 4 waves separated by a 1/4 cycle and 5 waves separated by 1/5 of a cycle. And then here we've got n waves separated by 1 over n cycles. And what I just want you to take away is that anywhere you look, you've got corresponding waves with positive and negative amplitudes, all right? And so you're always adding plus and minus everywhere along here. And that's why if we have n waves with phase shifts of 2 pi over n, we are getting perfect cancellation. Now, here's one problem. If we take into account the fact that we are not really getting just a perfect, we're not getting uniform spread, we're getting a sinc function from each slit. Well, let's see, I've done something where, oh, I flipped this around. I said A is the grading period. I don't like that. Let's make this notation consistent. Some books flip it around. All right. D is the grading period. I missed something.
You have to swap the KA and KD on the plot as well.
Oh, yeah. All right. So we're getting less and less signal in each peak. And even without doing a detailed analysis of how the M value of the peak affects your resolution, you can already see that, well, we're getting the most at M equals 0. And M equals 0 is the least desirable of all the peaks, because M equals 0 is the peak that all wavelengths go to. It's the one where you get absolutely no discriminating power. And why that happens, D equals 2.8, KD 2D. I will post a revised file after class.
You can swap the KD on the second line there to KA as well.
Oh, yeah. Thank you. All right, the basic way to think about this is that if I overlap a sinc function with the gradient intensity, I'm getting the two of them matching each other pretty closely, all right? And so basically this is the product of two things. This gradient function here is the product of a bunch of spikes that, if it weren't for the sinc function, would all have the same height, as we saw up here, and a sinc function that's decaying. And so that's why we're getting less light at the different M values, at the higher M values. And that is important. By the way, we can also, if we wanted to, instead of writing out a sum, we could do an exact calculation. The sum of e to the minus I m phi, we could use the sum of x to the m. And the sum of x to the m would be 1 minus x to the m. Sorry, 1 minus x to the n, where n is the number of terms in the series. You might say, well, it's not going to n, it's going to n minus 1, but it started from 0. Over 1 minus x. And if x is e to the minus I phi, then we could get this. And the intensity will be E star E, or proportional to E star E. We multiply all of this through, and we're going to get 1 minus cosine of n phi over 1 minus cosine of phi. And that is 0 if cosine of n phi is 1 and cosine of phi is not equal to 1. So this is another way of understanding all of those points where we get destructive interference in between. Any questions? Okay, so some practicalities. First of all, manufacturers rarely tell you D. What they tell you, it's not that they're trying to hide, it's just that the common notation is lines per millimeter. So they will usually say like, I don't know, 100 lines per millimeter. That would be a millimeter divided by 100 or a 10 micron spacing. If we had a very large spacing, we will get many peaks at 2.9 degrees, 5.7 degrees, and so forth. Another practicality is, let's say we're working with that same grating, and instead of using 500 nanometer light, we sent in some ultraviolet light, 250 nanometers. Well, then we're going to get peaks whenever sine theta is, instead of being an integer multiple of 0.05, an integer multiple of 0.025, which means that we wind up getting peaks when sine theta is 0.05. So one of the peaks from the 500 nanometer light overlaps one of the peaks from the 250 nanometer light. And this brings me to a story told by a friend who was working at a company that makes diffraction gratings. A customer told him that they need a grating that can tell the difference between 600 nanometer light and 300 nanometer light. And my friend was torn because that's physically impossible, but when you work in sales, the customer is always right. Anyone have an idea of what you might do in that situation beyond, talking to the customer, but talking carefully to the customer, but what a technical solution might be? One thing I would do is, of course, you could look at the two different peaks, but usually these things are set up to only look at one peak or only look at one range of angles, because if they look at a second range of angles, if they look around all of these angles, then they know that anything they see up here should be redundant with it. But if I looked at both of them and I got different intensities at these two and I corrected for that sync function or whatever, that would be one way. That's hard. Can anybody think of a much simpler way to disentangle this? How about do the measurement twice? Once with a filter in place that blocks one of the wavelengths and transmits the other, and once without that filter. I mean, ideally you'd do it with two filters. First one that transmits one and blocks the other, and then a filter that swaps around. If that's not practical, then just do it with one filter and look at the difference between those two spectra. That's what I would do. Now, if they wanted to make an automated product, that's a little bit harder. But if they're going to have to, they're going to have to increase the complexity of their product. But if this was just for some laboratory testing, then yeah, I just do the measurement twice, once with a filter in place, once without. All right, so a grating can't work for all wavelengths, partly because of that issue of integer multiples. If you could work at this angle, it's going to also work. If it works for this wavelength, it's going to work for half that wavelength or twice that wavelength. Also, if lambda is larger than the grating period, then you won't get any peaks. All right, so let's talk about the resolution of these things now. We've got peaks that have finite widths. And so what is the width of that? Well, delta phi was, and here I realized I should have written this out a little more explicitly. So let me switch to something where I can write freehand. Zoom. I'm going to share the screen. All right, so we've established that we get a peak and then we get a trough if the change in phase was 2 pi over n. That's the change in phase, which is delta kd sine theta, which is 2 pi d over lambda delta sine theta equals 2 pi over n. You can cancel our 2 pi's and we get the delta sine theta is lambda over n d. Any questions on that? Okay, so there's two different delta thetas. There's the delta theta, or delta sine theta is lambda over nd, and that is of course going to be partial sine theta partial theta delta theta, and the derivative of sine theta is cosine theta. So what we're going to wind up getting is that delta theta is lambda over nd cosine theta. And this is the delta theta, it's really here. This is the delta theta due to the peak width, okay? Now, there is also a change in theta when we change the wavelength. I go back to my notes. All right, there is the change in theta when we change the wavelength. And that's going to be partial theta, partial lambda, delta lambda. We can get that by using the fact that sine theta is m lambda over d. And we'll just take the derivative of both sides with respect to lambda. Now on the left side, we'll have to use the chain rule. The derivative of sine theta with respect to lambda is the derivative of sine theta with respect to theta multiplied by the derivative of theta with respect to lambda, or cosine theta, partial lambda. On the right-hand side, well, taking the derivative of all this with respect to lambda is much simpler. M's a constant, D's a constant, so we get M over D. So cosine theta, partial lambda is M over D. Partial theta, partial lambda is M over D cosine theta. So delta lambda, partial theta, partial lambda, the change in where the peak is when we change the wavelength is M delta lambda over D cosine theta, and that's got to be larger than lambda over nd cosine theta to tell the two lines apart. Basically, if I change the wavelength, I'd better move this peak far enough away that it's not overlapping the original peak. And technically speaking, there's no such thing as zero overlap. There's always tiny tails. And if we really start getting into the statistics of it, we can start debating, well, just how far apart do they really need to be? And the short answer is that if you've got good signal to noise and really good detection, then in principle, any difference is resolvable. And you're thinking, wait, that sounds too good to be true. Yes and no. I said in principle, and I said if you have good enough signal to noise. So if you have really, really good signal to noise, then yes, you can tell almost anything apart. but really, really good signal to noise might be insane. All right, it might be a very large number of photons. It could be 1 million photons. So, and then you'd better have a really good model of the electronic noise in your camera. So I said in principle, but in practice, you are guaranteed to be able to tell them apart or as close to guaranteed as anything in science can be, if these two peaks are separated by more than the width of that first node, and then the second peak is at least somewhat resolvable. I've drawn these two peaks having the same height. If the nodes of them are no longer, if they're far enough apart that the node of this one is overlapping the node of the other one, then the only real question remaining is do you have any signal at all in one of these peaks? If you've got any signal that rises above background noise, then you can tell. So if the peaks are far enough apart that that their shapes aren't overlapping, one of the peaks is well above background and the other peak is at least somewhat above background, then you can tell. That's a very easy, safe statement to make. It's a statement that everyone goes for. I happen to work in a field where people have done a lot of work on, in principle, how well could you resolve two peaks? But even there, even if you go to all the really big gurus of statistics and machine learning, they'll still say it's better to just have these two peaks cleanly resolvable. Any questions? All right, so we can use a grading if m delta lambda over d cosine theta is bigger than lambda over n d cosine theta, or delta lambda is bigger than lambda over mn. Any questions on that? People will sometimes write that as lambda over delta lambda equals mn. That's essentially, and they'll say that's the number of wavelengths you could resolve, because you could say we've got a range lambda, we can divide it into little segments of size delta lambda. Now in reality, you're never detecting from 0 to say 500 nanometers, because something that was 0.1 nanometers is a gamma ray, sorry, not a gamma ray, an X-ray. But, if you're detecting over a range that's comparable to the wavelength, 400 to 700 nanometers, rough approximation of the visible range. That's a width of 300 nanometers. That's comparable to the center wavelength. So if you were sampling across the visible spectrum, you could take that width, which is comparable to lambda, divide by your resolution, and that will be equal to the order m multiplied by n, the number of slits that you're actually sampling. All right, the time I budgeted for this, we're ahead. So let's keep going a little bit. Why is this there? Okay, so again, the resolution analysis, but that's not the end of the story. Large N is good. Large M is also good, because large M is also good, and d sine theta is m lambda. So M would be d sine theta over lambda. So you might say, oh, well, then we must want large slit spacing d. Well, let's see here. The width of the grating is going to be the number of slits multiplied by the spacing. Or if I took the width and divide by the spacing, I'd get how many slits fit in there. So W over N sine theta equals m lambda. So M times N, the thing that we established before, we said that delta lambda over lambda should be greater than or equal to 1 over mn. Mn, the figure of merit that we care about, is W sine theta over lambda. Now W is fixed by your instrument. You've set up your optics to spread that light out over as wide of an aperture as you can. So that's fixed. Lambda is fixed by what you're working with. Then clearly we want a large sine theta. One way to think about that is that when you have a large sine theta, you have a large change in angle. When you have a large change in angle, you have a large change in k. And so when you add up waves with two different k vectors coming at two different directions, you're getting a very sharp effect on the screen. Okay, making a large grading is easy enough. Large sine theta is not too hard. Just pick the right values of lambda and d. But as I said before, we are playing around with the sinc function. And that sinc function is sending most of the light to 0, and then it's sending a little bit of light to this part and a little bit less light to that part. That's the problem. The problem is that if we just simply had slits illuminated at normal incidence, we send almost all of our light to m equals 0, and there's nothing more to say. And you could start saying, well, hey, let's make the slits really narrow, because if we make the slits really narrow, then we send this light out to larger angles. Can anybody think of a problem with making the slits really narrow?
Do you start blocking more of the light from getting through if they get too small?
Yep. There was another comment on manufacturing. That could also be a problem for sure. There could be a manufacturing problem. But even if we solve that manufacturing problem, we've just lost signal to noise. So that's not good. All right, so one thing we could do is a reflection grating. We could have something that is corrugated, so it reflects in many directions, all right? And so again, we've got D, the spacing between the corrugations. We've got theta I, the angle that it's coming in at, and theta R, the angle it's reflected at. And now they are not necessarily the same. The way to think about this is once upon a time we stored information on things called CDs or DVDs. And when you look at a CD or DVD, you don't just see the head-on specular reflection at angle of reflection equals angle of incidence. You see reflection at many angles. You see many colors coming off at many angles, all right? Because each of these corrugations starts spreading the light out. And we can then work out, again, what's going to happen. Well, if I have light hitting this corrugation and light hitting that corrugation, the path difference here will be d sine theta I. And if I look in reflection then, light coming off of this corrugation and light coming off of that corrugation, the path difference will be d sine theta R, where theta R is the angle of reflection. And the upper slits are ahead because it was a short distance in the reflection, but they're behind for the incidence. And so the phase difference is d times delta sine theta, the difference between sine of theta I and sine of theta R. So d sine theta R minus d sine theta I, that's m lambda. Sine theta R is m lambda over d plus sine theta I, and y. Okay, now let's, so I don't know what is going. This is behaving weird. Okay, but now we still have this problem of how is light distributed among the reflection angles. So let's look at a single reflector element here. All right, we've got the center path, actually, the element goes from minus a over 2 to plus a over 2. So we're going to have the center path here and an off-center path. That path difference will be y sine theta r minus y sine theta I. So again, the path difference is y delta sine theta. And we integrate that over the entire aperture, the opening of this reflector, from minus a over 2 to plus a over 2. And we've done this integral before, and we got a sinc function. We got the same sinc function as before, right? And so that doesn't seem to help because we get a sinc function. It's just now it's peaked at when theta r equals theta I, so the delta sine theta equals 0. It's still the m equals 0 peak. It's just that we've shifted the m equals 0 peak to a different angle. But there's a trick coming. We're going to add a third angle. We're going to have all of these reflectors tilted. And that's actually pretty easy to do. When you etch grooves to the surface, you etch the grooves with a tool that's at an angle. And they call this a blazed grating. I think it comes from the same word as emblazoned, you know, a symbol emblazoned on a surface. So we've got this blazed grating. Now, we can measure theta I and theta R in two different ways here. If I'm just asking about reflectance off of this element, I'm ignoring the fact that I've got things down here. I just want to ask about reflectance of this element. I get my peak reflectance when it's making a specular reflection off of here. When the angle, not between this normal, the normal to the direction that it's periodic along, but rather the angle here. If I were to look at this angle, if I were to look at the angle from the normal to the reflective element, I want the angle of incidence as measured from this reflective element to equal the angle of reflection as measured from that reflective element. But if I want a diffraction peak, I want the angle of incidence as measured from this vertical surface to be related to the angle of reflection via d times delta sine theta equals m lambda. So the angle that goes into that diffraction formula is no longer the angle that goes into the reflection formula. Right? So the angle that's determining maximum reflection can be 0 for this purpose, or the change in sine theta can be 0 for this purpose, reflection off of a single element, but the change in sine theta could be non-zero for this purpose, interference between these elements, because we're measuring those two angles with respect to different normals, with respect to different perpendicular directions. Any questions? Anyone? Okay, so what we get is that the angle with respect to the reflective element is going to be theta r minus theta b, because if we look over here, this is theta r. We're still defining theta r with respect to this horizontal line, which is perpendicular to the vertical. So this is theta r, okay? Theta r goes from this horizontal line to whatever direction the outgoing wave is. But when I look at the angle with respect to that reflective element, that's theta r minus theta b. And theta r minus theta b should be equal to this angle, theta I plus theta b. And I haven't really drawn it that way, but let's just pretend. This angle should be equal to this angle if I want to maximize the reflectance off of this element, because this angle is theta I plus theta b. This is theta r minus theta b. These two should be equal, or theta r minus theta I should be 2 theta b if I am maximizing the reflectance of this element. So what I've just done is I've said, okay, if I want to get as much light as possible coming off of this element, the angles of reflection and incidence should satisfy this rule. Okay, so I maximize the reflection off of that element. Now the question is, will the light reflected off of this element, which is really strong light, I get a whole bunch of light coming off of this element, and I get a whole bunch of light coming off of this element, and a whole bunch of light coming off of this element. Will these waves add up constructively or destructively? Well, now we have to satisfy this equation, right? So we've got two equations, two unknowns. We can set it up to satisfy both of them so that we get very strong reflection off of each element, and we get very strong constructive interference between each element. Any questions? So there's a few geometries that you could do this in. Sometimes they send it in just perpendicular or nearly perpendicular. One disadvantage is that some of this light is going to hit this little corner here, and if there's any surface roughness there, you're going to get scattering. An alternative sometimes is to work with a back reflection geometry, which, depending on how you do it, might sometimes minimize the scattering. It depends on the profile of these edges. If you work in a back, and you might be thinking, well, why would I work in a back reflection geometry? Remember, that's m equals 0 as far as this one element is concerned. But when we look at the phase shifts between these elements, it's a different story. As far as the phase shifts between these elements, theta r is minus theta I. So you get a very large delta sine theta. Now the problem, of course, is that we've got the light coming in, we've got the light coming out. Your detector and source have to be very close to each other. That's not always convenient. You could put in a 50-50 beam splitter here. All right, so the light comes in, but then we've got a beam splitter tilted at 45 degrees. It goes that way. What's the problem with the beam splitter? Any guesses?
Is it
Sacrifice
the noise
what?
again?
What?
Is it the signal to noise again?
Yep, you sacrifice 50% of your signal coming in, and you sacrifice another 50% coming out. Some people use holographic gratings. Basically, they use light to pattern a surface. When they pattern that surface, you get something very gentle. There's absolutely no surface roughness here, or hardly any surface roughness. If you're worried about contamination, you're worried about light spilling out into other channels, this is as close as you're going to get to zero surface roughness, so zero crosstalk between channels. The problem is that you're usually working off of some sort of reflective plastic surface. Well, reflective plastic isn't that reflective. And so because it's not that reflective, what winds up happening is that you get a whole bunch of transmission. You sacrifice signal to noise, but you avoid crosstalk between channels. That could be worth it. It all depends on your application. Finally, let's talk about how people use this in practice. So you got a little point source, you got a little specimen. Okay, your specimen is sending light in all directions. So what people will do is they'll take a specimen that sends light in all directions, and they'll place it one focal length away from a curved mirror. So it hits the curved mirror. You got a source, as long as it's a small point source, one focal length away. Well, all of that light gets collimated. All of that light is coming in at the same angle. It all hits the grating at that angle. It comes off the grating at a range of angles, and what angle it comes off at depends on the wavelength. So let's just look at one wavelength right now. You got one wavelength coming off at an angle that was chosen to satisfy all of our conditions. Of course, it's all going at the same angle. It's spread out over a range of positions in space. Well, we got a bunch of parallel rays hitting a curved mirror. When parallel rays hit a curved mirror, they get focused to a point. And that point is an off-axis distance y equals f tan theta. So theta over here depended on wavelength, which means theta here depends on wavelength, which means y depends on wavelength. Any questions? All right, that took a lot less time than I thought it would. So here's what we're going to do. So we're way ahead on topics. On Thursday, I'm not going to do photons. Instead, on Thursday, I'm going to do something called photonic crystals. I'm going to talk about systems that combine the concept of a grating and a multi-layer film. This will just sort of be for your edification. It's a concept that has been around for a while in various forms. It got synthesized in the 80s by two very different people working on two very different problems with two very different interests. Then, like all fascinating physics to come out of the US in the 80s and become trendy in the 90s, we promptly learned with the fall of the Berlin Wall that somebody had allegedly done it in the Soviet physics literature decades earlier. I don't think there's any physics discovered in the West that someone hasn't claimed was discovered in the Soviet physics literature decades earlier. So I'll just talk about that because it's a fascinating topic that combines concepts from diffraction gratings, multi-layer films, semiconductor physics. It's getting used in a lot of devices these days. The next week, we are way ahead of schedule. So next week on Monday, I'll give the lecture I was originally going to give on Thursday about photons and fluorescence. So on Tuesday, I will give the lecture I was going to give on Thursday. Then on Thursday, what I think I'll talk about is Bell's inequalities, because Bell's inequalities are a really deep test of the nature of light and photons. And they're also a very nice application of the polarization of the polarizing beam splitters, the polarizing multi-layer film beam splitters that you're working on for your final assignment of the semester. You're not working on them for next week, but for the following week, you'll be working on that. So I'll talk about the Bell inequalities. Then in the final week, on that Tuesday, I will talk about some sort of biomedical imaging application. It might be multiphoton microscopy. It might be something else. I'm still debating whether to switch that around. And then on the final Thursday of the semester, I will talk about your final project assignment, which is due 1 week later. And for now, I'll just make myself available if anyone has any questions about the Python program or the upcoming assignment. Otherwise, I'll see you Thursday morning. Bogdan, you have any questions for me?